Math 2414, representing functions as power series, video 8, fifth example, integrating to create a power series. I haven't checked it yet, and I won't be able to until I finish recording the videos, but I think on the previous one, I accidentally said fifth example when I meant fourth example. If I did, it should have a correction listed in the title of the video. All right, so anyway, we're going to find a power series for the following function, and we're going to determine the interval of convergence. The function is f of x equals a natural log of x plus 1. Now, how are we going to do this? Because the only tool that we really have at our disposal right now is that a over 1 minus r is equal to the sum n equals 0 to infinity of a times r to the n when the absolute value of r is less than 1. Up until now, most of our functions, not all of them, but most of our functions already had some type of structure similar to this. The only one that was really different was in the previous video where there was a square that we obtained by differentiating something. So how are we going to make this have the correct structure at all? Well, that's equivalent to asking, what can we do to this to make it have a structure that looks a little more like that in terms of calculus? Well, the first thing that comes to mind with me is if we differentiate this, if we take the derivative, so I'm going to draw a little arrow pointing down and say, let's take the derivative. Let's see what we would get. The derivative of this, f prime of x, will be 1 over the inside, so 1 over x plus 1, times the derivative of the inside, but the derivative of the inside is 1, so the derivative is done. And if you notice, the derivative has the correct structure. It is 1 plus x. Now, it doesn't look exactly like it because it has a plus instead of a minus, but we've dealt with that before. All we have to do is rewrite the plus as minus and negative. Make that a little clearer. There we go. And we can instantly identify the first term as 1 and the radius is negative x. So the series that we get is the sum of n equals 0 to infinity of the first term times the radius to the nth power under the condition that the absolute value of the radius, ratio, I should say, not radius, 1 times the first term times the radius to the nth power. So 1 times negative n to the nth under the condition that the absolute value of the radius is less than 1. Well, that means that x is between negative 1 and 1 in this case, so let's not dilly-dally there. What I would like to do, however, is get rid of all that and rewrite my power series with an x to the n, not a negative x to the n. So we can rewrite it as n equals 0 to infinity of negative 1 to the nth power. I'm going to do something real quick. I'm going to try to grab all of these drawings and move them. See if I can move them without distorting them. Well, that didn't work. Let's try it again. Not you. Did I grab everything? No, I didn't. I missed a parentheses. I grabbed some of the sum, but I don't care. Okay, everybody move. No. I'm going to pause the video and get this to look right. Hold on. Okay, that looks a little bit better. So as I was saying, we took the derivative of our function, recognized that the derivative had the correct structural form to resemble the sum of a, hold on folks. The derivative had the correct structural form to look like the sum of a geometric series, a power series, if you will. And so we manipulated it until we could identify the first term in the ratio so that we could set up the sum. And I was in the process of rewriting the sum as a coefficient times the power of x. So we're taking this negative x to the n and giving the nth power to the negative 1 and to the x. The 1 in front was precisely that, a 1, so we don't have to worry about it. But this is not this function whose series we were looking for. This is the series for the derivative of the function. We want to know what this guy's series is. Well, all we have to do is undo what we did to get started. We started by taking the derivative to get the series for a function. How are we going to push it back up? In other words, how are we going to take this series and turn it into the series that we want? By undoing the first move that we did. The first move that we did was we took the derivative. Now we need to undo that by taking the integral. So we need to integrate -1 to the nth power x to the n dx. And that will give us the term that we add for our power series, for the term for the power series for the function we started with. That looks tricky to integrate until you realize it's a dx integral and the n is completely independent of it. So we just got to focus on the x and leave everything else alone. The -1 to the n is a constant relative to x, so it just sits there. And the integral of x to the n is 1 over n plus 1 times x to the n. Now, we did just take an indefinite integral, which means we do pick up a plus c. So here's where we are. We have this function is equal to this series. By taking the derivative of the function, finding its power series, and then undoing the derivative by taking the antiderivative, the integral, with a plus c. Now, let's talk about interval of convergence first, and then we'll worry about the plus c. Our interval of convergence on our power series, I had mentioned it, but then I erased it because it was in the way. We need the absolute value of the ratio to be less than 1, but this just gives us -1 is less than x is less than 1, which means that our interval up here will start with this, but we will have to check convergence of the endpoints individually. That's what our theorem said. Integrating or differentiating doesn't change the interval. It just might change which ends you pick up convergence on. Let's move this to the next page so that we can figure out the c, and then we will figure out whether or not it converges at -1 or 1. All right, our sum is the sum of n equals 0 to infinity of -1 to the n times 1 over n. Let's go ahead and, times 1 over n plus 1. Let's just put this over n plus 1, and then times x to the n plus 1. And then some constant. You know what? Having that constant at the end of the sum can be misleading because it does look like that it might be inside the sum. In other words, it might get misinterpreted like that when it's not. The plus c is actually outside the sum, and the easiest way to make it outside the sum is to not put it where the sum is. So let's just move some things around, and we'll put it at the beginning. It's okay to have it at the end, but it can be a little ambiguous if you're not careful, and I would like for it to not be ambiguous. Okay, let's figure out what the c has to equal. Now, how are we going to do that? Well, this series is supposed to equal to that function on this interval, and we'll check the endpoints in just a moment. -1 less than x is less than 1. So if we get convergence on that interval, we should be able to pick any number in between, plug it in. Gee, I wonder what number I should plug in. How about 0? Not because it's 0, but because it's the center. If we put in x equals 0, we get c plus, actually before we do that, it'll be easier to see. Before we do that, let's expand this sum. Let's put in n equals 0. That gives us -1 to the 0, which is 1, over n plus 1, so over 0 plus 1, times x to the 0 plus 1 times x to the first. Well, that's just a fancy way of saying plus x. If we put in n equals 1, then we get -1 to the first power, which is -1, over 1 plus 1, which is 2, and then x to the 1 plus 1, which is 2. We put in n equals 2, we get -1 squared, which is +1. We get 3 in the denominator, and we get x cubed. Next one would be -1/4 x to the 4th, et cetera, et cetera. And let's let x equal 0. Because 0 is the center of the interval, the center will kill off most of the terms. In fact, it's going to kill off all of them, except the plus c. Feel kind of silly writing all these terms over here, knowing full good and well that they're going to vanish. All right, everybody who's 0, get out of here. You're gone, all of you are gone. And the only thing we're left with is C equals the natural log of 1. But guess what the natural log of 1 is? Shouldn't have to guess. You should know that it's 0. So our constant of integration is actually 0, which means that we can replace 0 with it, and now we have something that looks like this. Sum n equals 0 to infinity, negative 1 to the nth power over m plus 1 times x to the m plus 1. Now, we could play some substitution games to make the exponent a single variable instead of m plus 1, but let's not worry about that right now, because we are still focusing on convergence. We have to check convergence at the endpoints. Anytime you differentiate or integrate a series, you don't lose the interval. You may pick up or lose endpoints. Well, in this case, we would have to pick up because currently prior to integrating, we didn't have convergence at the endpoints. But let's check x equals 1. At x equals 1, I'm not going to put it into the natural log because that's not where I'm checking convergence. I'm checking convergence on the series. If x is equal to 1, we end up with negative 1 to the n over m plus 1. And it may not look like it, but that's the alternating harmonic series. I know the harmonic series has an n on the bottom, but it starts at 1. If we were to substitute n equals 0, we would get 1 over 1. If we put in n equals 1, we get minus 1 over 2. If we put in n equals 2, we get plus 1 over 3, minus 1 over 4, dot, dot, dot. This is the alternating harmonic series. This converges. If you didn't pick up on that, you could also use the alternating series test, but regardless, this converges. So we do pick up convergence at x equals 1, but what happens at x equals negative 1? I'll tell you right now, I'm not expecting convergence because the function isn't even defined at negative 1. You can only take logarithms of positive numbers. But let's see what happens if we put in negative 1. We get negative 1 to the n times, remember we're putting in negative 1 back up here for x, times negative 1 to the n plus 1 over n plus 1. And that gives us the sum n equals 0 to infinity of negative 1 to the 2n plus 1, because we can add the exponents, over n plus 1. And on the surface, this looks like it's another alternating harmonic series. But I got some news for you. It's not. Why? Because negative 1 to the 2n plus 1 is not an alternator. I know it looks like 1, but it's not. How can I tell? Because this number is always odd. Think about it. An even number is defined as twice any number. So this number is always even. And when I add 1 to an even, it always becomes odd. So this is always odd, and negative 1 to an odd power is always negative 1. So that alternator does not alternate at all. It's always negative 1. Now, if the even odd argument kind of threw you for a loop, then maybe this will be a little more convincing. If I separate this into negative 1 to the 2n times negative 1 to the first by unadding the exponents, and rewrite the first one as negative 1 squared to the nth power by unmultiplying the exponents. Negative 1 squared is 1, and 1 to the nth power is 1. Negative 1 to the first power is negative 1. So again, that thing that looks like an alternator is not. It's just negative 1 dressed up real fancy, which means that this is equal to the sum of n equals 0 to infinity of negative 1 over n. We could pull out the negative if you wanted to. This is n plus 1 on the bottom. We could pull out the negative 1 in front if you wanted to, but even if you didn't, this is a harmonic series with or without the negative, and it's convergent. It's divergent. Therefore, we get divergence on this guy, which means that our original function, here comes the conclusion, natural log of x plus 1 is equal to the sum of n equals 0 to infinity of negative 1 to the n over n plus 1 times x to the n plus 1 on the interval -1, 1, including 1, but not including -1, because when x was 1, we got convergence. It's kind of buried in there. I'll highlight it. But when x was equal to -1, we got divergence. So we had to put a bracket on the 1 to indicate convergence. So here's an example of where we picked up convergence at x equals 1 when we integrated. Before we integrated, at the bottom, we had this series, which did not converge at x equals 1.